Welcome, it's our great honor to present you our new event-based endpoint linear solver for line and motion estimation. This is a joint collaboration between the Mobile Perception Lab at ShanghaiTech University and the Robotics and Perception Group at the University of Zurich. Traditional approaches to visual odometry usually rely on feature extraction and matching, followed by the application of efficient geometric incident relationships, such as epipolar geometry or trifocal tensor geometry. Towards feature extraction, events are often converted into intermediate, dense representations, however ignoring the temporal, asynchronous nature during the actual feature detection stage. Alternatively, adaptations of keypoint detectors operate directly on raw events, which preserves their natural properties but can be afflicted by noise. Both methods suffer from error compounding, as they separate feature detection, tracking, and geometry estimation. On the other hand, in man-made environments, given that events are primarily triggered by high-gradient appearance boundaries, the dominant feature for event-based motion estimation is lines. Since many such boundaries may be straight, line features have become very popular. We have seen a few motion estimation solutions utilizing these line features, which are sometimes extracted by detecting planes in the original space-time volume of events. However, this assumption of a planar distribution is, in fact, wrong. Estimating motion from event measurements remains an open challenge, as motion cues need to be inferred from the complex spatio-temporal structures formed by events, which traditional vision-based algorithms struggle to grasp. While the instantaneous reprojection of a line is still a line, the overall event cluster does not form flat planes in the spacetime volume, even in the case of pure translational displacements of the camera pose. Hence, as shown here, what we get is a twisted manifold. In our previous work published in ICCV 2023, we denote such a manifold as an eventail, which means foldable fan in French. Under a locally constant velocity assumption, this eventail manifold can be parameterized by camera velocity and 3D line-related parameters. It becomes intuitively clear that for a dynamic vision sensor, feature extraction and motion estimation can no longer be separated but need to be addressed as a joint model-based clustering problem. In our previous work, we defined an incidence relationship to characterize such an eventail manifold, where all events are triggered by points on a 3D line. This enforces that the orange-colored bearing vector intersects with the blue 3D line. It uses a non-minimal representation with 4 degrees of freedom. Additionally, this representation encounters singularities when describing lines parallel to the two planes. In contrast, this work introduces a new representation based on the angle axis representation. This representation is singularity-free, and depends only on 3 degrees of freedom as it implicitly enforces scale ambiguity. Similarly, the previous minimal solver is automatically generated based on the Grobner basis theory. It also relies on route-finding algorithms that are expensive to run and suffer from instabilities that are not easily detected. Then again, with the new incidence relationship, we derive a simple algorithm for determining motion and line parameters that only relies on solving a linear system and simple vector operations. This linear system can be easily extended to more than 5 events, with a minimal increase in complexity. Extensive experiments show that this new linear solver surpasses the previous one in numerical stability and operates over 600 times faster. Additionally, the quantitative examination indicates that the linear solver demonstrates lower error with noisy measurements, and this margin grows further in overdetermined systems. In conclusion, we are excited to introduce a new line-based solver for relative motion estimation using an event camera. This new solver can handle arbitrary sizes of events and operates about 600 times faster than its predecessor. Unlike traditional solvers for frame-based cameras, our method is built upon first-order dynamics, allowing it to incorporate temporally asynchronous data. This advancement not only enhances our understanding of the relationship between events, appearance boundaries, and motion, but also pioneers a new class of spatio-temporal geometric solvers. We believe there is significant potential for further exploration based on this novel approach. We invite you to join us for the oral session for a more in-depth discussion. Thank you.